Okay, so now we've got our N160. And what we're going to do is we are going to calculate the relative density based on that. So the equation for the relative density is this guy over here. And so we need the N160, and then we need these correction factors. So the first one is based on grain size, the second one age, and the last one is based on over-consolidation ratio. So for this one, we're just going to assume that the over-consolidation ratio is 1. We'll assume that this has been placed within the last 10,000 years, and so that'll be the correction factor there. And then we need some sort of correction factor for the grain size. And so we can look at different grain sizes, and so we have a well-graded sand, so our sand is going to be somewhere in between say 2 and 0.075, excuse me, 4.75 and 0.075 millimeters. And so we can use that in order to estimate what our grain size is. So one way to do this would be just to take the log of the two. So you could take the log of 4.75 plus the log of 0.075. Take that divided by 2. And so the average of those is, we'll have to do that again, 4.75 log plus 0.075 log is that. So the average of those two is negative 0.224, and then the D50 bar, the average of those two, 10 to the negative 0.274, around 0.6. So we could use that as an average grain size. So go back in here and we'll just say that our average D50 is 0.6. So now we just have these factors. We've got your CP, and we've got your CA, and your COCR. So COCR we're just going to assume to be 1. CA is just going to be equal to 1.2 plus 0.05 multiplied by the log the time, which we assume to be 10,000 years, divided by 100. And then we've got our CP, and that's just going to be equal to 60 plus 0.25 multiplied by the log of this value over here. Oops. And that's about 60. And now we can plug these into this equation. So here's our dr, and that will be just equal to the, let's say, if this is equal to nothing, then make it equal to nothing. Otherwise, it's equal to the square root of our D160 divided by our C sub P, C sub A, OCR. And just to kind of follow some of the same methodology as before, I will just say that this is the grain size correction. And this is going to be our age correction. This is going to be our OCR correction. So if this is equal to, oops, else square root, and then we've got our N160 divided by C sub P divided by your C sub A divided by your COCR, and we'll multiply the whole thing by 100. And I made a typo, didn't like it. So let's Hopefully it corrected me correctly. And there we go. So, and you can see a few of these are a little bit high. And that might be because we have excessively high blow counts for that value. Sometimes that sort of thing happens. Like over here, you've got a blow count of 155. That's an irrationally high blow count. But even the blow counts over here, 165. So some of the values might be more than 100, and that is okay. So we have our relative density. And then we could go through and we could determine what the verbal descriptor was for each one of those as well. So for example, if we go from 0% to 15%, then this is going to be very loose. And then if we go up to 15% to 35, this is loose. And then 35 to 65, this is going to be medium. And then from 65 to 35, 65 to 85, right? It's dense. And then greater than that will be very dense. So 0 to 15, very loose. 15 to 35, medium. 35 to 45, dense. 65. One more time. So 15 to 0 is very loose, 35 to 15 is loose, 65 to 35 is medium, 85 to 65 is dense, and greater than that is very dense. And so we can set this up as one more lookup table. This is equal to nothing, then make it nothing, otherwise look up. And we'll look up our value, which is at relative density. And then here's our vector. And here's our result. And there we go. So this gives us a verbal description. Now, what we can do is we can compute what our friction angle is, and we'll do this, the friction angle, as the last video of the SBT.